Okay, so hello everybody. Welcome back to our HAL tutorials. We continue with these tutorials every semester to introduce you to our whole system and to different ways to take advantage of it. And today I'm very happy to introduce Shiru Lu. Shiru is a research scientist in NCSA. He has a lot of experience in developing machine learning models and training them on HAL. And so today he is going to give a tutorial on TensorFlow, about how to get started with TensorFlow and how to use it. And this will be a hands-on tutorial. You can follow him by connecting to HAL and also running in the notebook and all that. So Shiru, please take it from here.
Thank you, Vlad, for the introduction. And thank you, everyone, to attending our workshop. So I have posted this Google Doc link in the chat. You can open it. So this might help for anyone who first attend our workshop. You do have to get account on HAL system. So during this training workshop, I will present some examples in Jupyter notebooks. You can follow me if you can use open up interactive Jupyter notebooks on HAL. So I give a few minutes. Try to open this link and log in the so-called HAL on demand. It looks like this once you log in to this page. And then fill out this. I think this one you have to use HAL training to make sure you get a interactive job very quickly. Also, during this workshop, if you have any questions, you can post on the chat. So yeah, once we're done with step 1 and step 2, you should be able to see something like this that you can open in your home folder. And then once the job started, you can launch an actual terminal. So all my Jupyter notebooks are in this GitHub repo. You can clone it into your home folder and then open it. So I give like 1 to 2 minutes for everyone to finish this. And let me know if you have any questions. has anyone is still working on the first 3 steps? Do you need more time? If you need more time, you can leave a message in the chat. I saw Pranav leave a message says you have some issue with store. Is this your first time to use HAL system?
Yeah, I haven't used the HAL system before, so I didn't have Duo configured.
Do you have an account on HAL?
I have an NCSA account, but I can't SSH in, and I also can't use the HAL on demand website.
In this case, you have to open an account first, a HAL account. If you see my screen, we have a HAL wiki page that can show you how to open an account. This might take some time, so you may not be able to follow this today, but you can try this out later. To request the access of HAL, go to the link I just shared on the Google Doc and then fill out this form. So once you have filled out this form, and our system admins will open accounts for you, and then you can use HAL.
Sounds good.
So Sagar, yeah, it takes a few minutes to get queued. And are you still waiting?
Yeah, I'm still waiting. Yeah, I think it's ready to connect now.
Do you, are you make sure that you use this name of reservation as well?
I just got connected. Thank you.
Oh, okay. All right, great. Okay, great. So I think I just start the tutorials. So once you have cloned the GitHub repos, you should be able to see a folder like this. So I'm splitting this workshop into a few Jupyter notebooks. So I start with the first ones, which is about TensorFlow basics, like tensors and variables and back propagations, etc. And then I give a few examples for each about classification and regression using Keras API. So let's start with very fundamentals. So you can open this so this one is very fundamental. It's about to introduce TensorFlow basics tensors. So first, let's import NumPys and TensorFlows. So the very basic operating units in TensorFlow is called tensors. The tensors, it's very similar to NumPys. Essentially, they are just multi-dimensional arrays of a uniform data type. The only difference is that tensors are immutable, and also tensors are running on GPUs, which can accelerate the computation. So I assume everyone is familiar with NumPy. NumPy is kind of very essential data structure for doing any computation or scientific computation, like machine learning using Python. So in TensorFlow, there are two concepts. One is tensor, the other is called variables. While conceptually, the difference is for variables, instead of like tensors as a concept of a constant, variables is changeable across different session runs. So they are constantly updated in back propagations. So mostly for a model, the weights and bias in a model or the hyperparameters are usually variables. For example, here I gave an example in linear regression. So in linear regression, you have a formula like y equal to w times x plus b. W is the weight, and x usually it's your inputs, and y usually it's your outputs, and b it's intercepts. So usually when you try to build a model, the x and y, which is your inputs and outputs, they usually are constant. So we would like to use tensor to save this data. But for w and b, these are the model parameters, and they are need to be trained and updated. So these two are usually are variables. We will give more examples in the following about the difference of tensor and variables. So I'll start with something. I start with very fundamentals about like creating the tensors. This is very similar to NumPy arrays. You can call this TensorFlow constant of a list or a list of lists, and if you print the tensor, you can see it says the tensor the data you created, it's a tensor data type. These are the properties of these variables. You can have the data type. You have in TensorFlow, you have float 32, also float 64 for float type, along with integers, strings, etc. And also similar to the NumPy array, you can have a shape of this tensor or the dimensions. So besides of this TensorFlow constant, you can also using other method to instantiate tensors. If your tensors are all zeros or ones, or the tensor are constant, you can use a shape to define the size and dimension of your tensor. And also you can generate like randomly sampled tensors using some distribution functions like normal distribution, uniform, and Poisson. And you need to give the let's check it. Something. Okay, sorry about the typos.
Oh, no, there's no typo in your document. It works just fine. It is possible that somebody mistyped something when he was.
Okay. Yeah, okay. Yeah, you can print out all the tensors and looks exactly the numbers and dimensions. So I think all this are very similar to NumPy. And the NumPy arrays and TensorFlow tensors are convertible. If you have a NumPy array, you can convert it to tensors by doing this. Or if you have a tensors, if you do tensor.numpy, it will converting the tensors into a NumPy array. So we introduced that there are two different data type, variables and constant. For constant, it's immutable, and variables are mutables. So we will show you this later. So now in this cell, I defined both the variable and tensor constant, and I named them. One is mutable and another is immutable. If you do this, and in this cell, what I try to do is that for this 10.7, I would like to assign a different numbers in the first element. And if I do this, now you can see for variables, which is mutable, it's changed from 10 to 5. But if I do the same thing for tensor, it will show me an error. So you cannot assign a different value to the elements in the tensors. It will say error message. So there are also other useful things about tensors, like math operations. They are all similar to NumPys, like adding, subtracting, multiplying, and matrix multiplications. So these three are elements wise, and the final ones are matrix wise. Yeah, you can also use symbols, which is equivalent to using functions. And there are more absolute functions like absolute and power in TensorFlow tensors. One thing might be useful to know is that oh, I think I have it later. So this is about indexing and slicing and reshaping. So if you have a big tensor and you only want to use a slicer with this, you can do like this. Is also the same in NumPy. So TensorFlow tensors and NumPy are very similar, and you can reshape it if you start with a range of this should give you 1 times 16, you can reshape it by giving this parameters. So the shape can be reshaped. You can also expanding the rank of the tensors and squeeze the redundant dimensions. So this you can find them very useful, especially if you're dealing with image applications. Sometimes images 1 channel, sometimes images 3 channel, or multiple channel, depending on your model type and the data type. This T function can be very handy. Yeah, one useful thing to know is that for math operations on variables, it will return a tensor. And you can also name each variables. So we just covered the very basic and fundamentals of TensorFlow variables and tensors. Next, I will give examples of automatic differentiations and regressions in TensorFlow. So there's a concept called a gradient tape that the TensorFlow provide this gradient tape API for automatic differentiations, which is to compute the gradient of computation with respect to some inputs. Usually the inputs are TensorFlow variables. During the calculation, the TensorFlow will record relevant operations inside of the context of the gradient tape. Then the TensorFlow use it to compute the gradient of a recorded computation using reverse mode differentiations. So I show this very quickly. So if we start with a variable with initial value at 5, and you have this gradient tape, this content manager, and you say y is equal to the square of x using TensorFlow function square, and you can get the gradient of this tape in terms of y of x. And because it's y is the square of x, and the derivatives is 2 times x of square, so you can see the derivatives that the computation is giving, it's 10. It's 2 times 5 in 10. So that's the functionality of gradient tape. Okay, we can run it. Yeah. The gradient tape tracks only variables by default. It will not track the TensorFlow tensors. However, it is also possible to track a constant tensors by calling an actual function watch. So similar to the above examples, now we change the type of x from variables to constant. And if you are not adding this line, you will not getting a derivatives here. By adding this watch, it will allow the gradient tape to track a constant tensor as well. Our last examples are given just a single inputs, but the gradient tape also works on list of inputs on either scalars or high dimension tensors. So in regression, you have the weights and bias. So there are two variables. If in this context manager, we define y to be x times the weights plus the bias, and we define actual variable z equal to the square of y, and you can get the gradient of z with respect to a list of inputs and print out the derivatives. And also for the calculation of the gradient, once it has been run, the calculation is done. Even you change the variable later, the calculation of the gradient will not be updated unless you tell it to update it. So let's keep going on. And for the above examples, I only give first the derivatives calculations. Now we can, it's also possible to compute second order derivatives with lasted gradient tapes. So for example, you have distance equal to half times the accelerator and the time squared. Your velocity is the derivative of distance to time, and your accelerate is the derivative velocity to time. So you can define time as a variable, and the accelerate is a constant. And in the context manager, we have a lasted ones, out tape and the inner tape. So in the inner tape, we have distance equal to this. And then when you do the speed is a gradient of the distance to time. And in the out context manager, you can have the acceleration equal to the gradient of speed to time. So this allows you to do the lasted structure, allows you to do second order derivatives. Now we have finished the backpropagation, using backpropagation to calculate the gradient. The following I give examples of how we can use that for a linear regression. So we will start with creating our data. So we have we use NumPy arrange to create an array of x ranging from 0 to 17 with step 1. And our y is 2 times x plus some noise. And we plot them out. And here's how it looks like. So we would like to do a regression model on top of this data. So to start with, we have some initial value for our weights and bias by randomly assigned ones. And we create TensorFlow variables for our weights and the bias with the initial value we just created. And here we are converting a NumPy. So X and Y, remember it's our inputs and outputs data. We converting them from NumPy to a TensorFlow tensor. In the alpha and epochs are the learning rates and number of iterations to perform the gradient descent. Then we have a loop to training our model. So in this gradient tape, we define the Y production to be, this is standard linear regression. And we calculate the loss. The loss will be the reduced mean of Y, which is the true outputs, minus the predicted Y. So this is like root mean square. And outside this context manager, we calculate the gradient. This will be useful for us to update the weights and bias. So here we are updating the parameters by using assign sub, so which is equivalent to subtraction. So W equal to W minus alpha times the gradient. And we are outputs our losses every 1,000 steps. And you can see the model will be training, the loss will decrease. And eventually, once the model is trained, we can plot out the predictions against the raw data. And this is how it looks like. So by now we'll be done with the TensorFlow basics and the fundamentals. Do you have any questions? If you do, please leave. You can open your mic or you can leave a message in chat. So all the purpose of this Jubian notebooks is to get you familiar with TensorFlow basics. Mostly it's to show how similar the TensorFlow to NumPys. If no questions, I would like to continue on this one. So starting from now, I would give examples on using TensorFlow for classification and regression. So I assume everyone is familiar with classification and regression, but if not, classification is more like you're predicting categorical outputs. Like if we have to differentiating orange from apple or a dog from a cat. This is classification. But if your model want to predict something that is continuous, like a temperature or a probability or a price, something like the value are continuous, then you need a regression model. But for both classification and regression, the steps in modeling are the same. You have to get your training data ready first, right? If you have a tabular data, or sometimes people working with videos data, audio data, or text data, or image data, you have to turn them into a multi-dimensional array, and then turn them into tensors. So that's step 0 to get data ready. And then we have to create a model. You can define the, so remember now we're dealing with deep learning models. You can preload a pre-trained model that someone already defined for us. For most applications, you can easily find a pre-trained model. Or you can define it by yourself, like the network architectures, the input size, the output size, like the number of hidden layers, etc. Or you can preload a pre-trained model and then modify it on top of that, on top of this pre-trained model. So once you have a model architecture defined, then you have to specify how to compile this model, right? How to update the model hyperparameters, the weights and bias. To do this, the most important is you have to define your loss function. In the following examples, you will see for regression or for classification, they have different loss functions. If you're working with something like natural language processing, depending on your applications, you will easily find there are more sophisticated loss functions. But essentially, loss functions is a measure of your model's production outputs versus the true outputs. If the loss is big, that means the model's prediction is very different to the true data. You have to keep working on the model until the loss is small enough. That means your model's prediction is close enough to the true label or true data. So loss function is kind of very essential. And then you also need to specify optimizer. So optimizer, it's there are a couple common ones, like mostly you will hear about stochastic gradient, a mini stochastic gradient, or atom, like this. Usually these optimizers are well studied. You can in TensorFlow, they have compiled most common optimizer that you can choose. And the third one is an evaluation matrix. So this is to evaluate your model performance. So the loss function is only used for training your model, but it may not be as intuitive to interpret your model performance. And this is only one single measure for the loss. In the evaluation matrix, you can have multiple metrics to evaluate your model's performance. And you can rely on this matrix to tell how good your model is performing. So these three are very essential for a model, you have to specify them before you train a model. So now we have defined the model architecture and how to compile a model. Next is how to feed a model. So the feeding the model is let the model do the work, right? They try to find all kinds of the optimized weights and bias. And so once step 3 is done, you have to look at your metrics and see how your models performed and decide if you need to improve the model through more experiments, right? Which is usually called hyperparameter tuning. So in your model, like you may have different options or loss functions or optimizers. In optimizers, you have learning rates, along with many other hyperparameters. You have to redo the experiments a lot of times to find the best ones that give you the best metrics. And finally, it's very useful to visualize the results and interpret the results and save your trained model. So you do not need to retrain it again every time you do the inference. So that's the steps in modeling with TensorFlow. This frame I think it's in universally the same for all kinds of model. It's also very familiar with other machine learning ones, like if you work with regression or random forest, the steps are quite similar. So, okay, let's get started. I start with a very simple regression. So we did this regression example in the last Jupyter notebooks by using the gradient tape. You can see it's not as intuitive. So the good thing about TensorFlow is it provides a lot of APIs for you to use, especially Keras, which is very powerful. It basically covers all the common applications. Instead of writing your own gradient tape, you can easily using the Keras API to define your neural network architectures and compilers and running the job. Similarly, we will start with creating the training data. So our X is ranging from 0 to 20 with step 1, and Y still it's 2 times X plus some noise. And then we are preparing this to inputs and outputs data and converting them to TensorFlow tensors. And we are plotting them here. You can see we can expect a regression model Y equal to 2 times X. So the step 1, as we mentioned, is to create a model architectures. So here we use a Keras API. It's called sequential, which is a sequential of layers. So here for regression, we only need a dense layer with 1. Right? We only want a very simple regression Y equal W times X plus B. So the step 1 is very intuitive. And once we define the model architecture, we'll start working on compile the model. So in compiling the model, you need to give the 3 essential parts of the of compiling a model. That's the loss, optimizer, and metrics. So the loss, we use MAE, which is a mean absolute error. So this is a common loss for regression applications. And optimizer, we use Adam with a learning rate of 0.1. There are only also other options, but here we use Adam. And metrics, we're only looking at the MAE. You can also have like MSE or other metrics as well. And once the model compile is defined, we can fit the model by using this fit. And here we also have to specify the number of epochs, which I have 20. And it will start training. And you can see the outputs of the training. For each epoch, it will output like, this is the speed of your training. If you have a big application, this thing is very important and can be very handy. You can have a good estimation of the time required to train your model. And usually the first epoch is more time consuming than the next ones, because in the first epoch you have to kind of initialize and set up everything from start. So the speed of the next ones, usually it's a more useful value for you to estimate the required time. And you can see the loss, it's smoothly reducing after each epoch. And the similar for your metrics MAE. So after 20 epochs, you can see your loss is relatively small, and they kind of converged in the last several epochs. The loss is not reducing significantly after step 16. You can also use the summary function to see your network architectures. So here we have a simple regression with dense 1. So only 2 parameters, right? 1 weight and 1 for bias. And once the model is trained, you can use the function prediction to predict. So giving X, the model has been trained, you can predict the Y. Ideally, it should be 2 times X. So we are expecting 20, but here it gives up 26 because of the noise. We have a noise for the outputs. And also, we're not fine-tuning our model. So this is the model outputs so far. You can also, so this is like the first version of our model. Usually, you don't know what are the best when you start to work on a regression model. So you start with something, and then you can try to find ways to improve the model's performance by tuning the model's architectures. Right, you can using different layers or number of hidden units. and also like activation functions, and how you optimize the model, or you just feed the model longer. So here I give an example of, instead of just using a single layer, we can stack a couple dense layers in the sequential functions, and then using a much smaller learning rate. So previously we have 0.1. Now we try something much smaller. So the learning rate allows you to train the model with smaller steps. It might take longer, and also previously we only trained 20 epochs. We can easily try a larger epoch number and retrain the model. And this is your model summaries. Now you can see the total parameters, instead of being 2, has been significantly increased, just because for the model we have more layers, and you can do the same thing in terms of prediction. So we can also predict a series of numbers and plot against the raw data, and this is for you to visualize how good your model performs. So just keep in mind, in practice, a typical workflow to build a neural net models is you start with a model and you feed it and evaluate, and you may not be very satisfied with the performance, and you tweak it and feed and evaluate again, and tweak it and feed it, evaluate again, until you find there's no easy ways to improve. So that's a simple examples of using Keras for regression. Before we start with the second one, do you have any questions? Okay, if not, we start the second. So in our last we give example of regression. Now we start with more details for creating a model. So for regression or for classification, usually if you have a data, we have to split the data into 3 categories: a training data set, a validation, and a testing data set. So the difference that for training your model, you want to use only a part of the data, and you keep the remaining of the data invisible when you're training it. The reason, because in practice, when you use your model for inference, this data is not going to be accessible for you to train it. So a typical way of building your models is we split the data, like 70% of them as training, and the 15% and 15% for validation and testing. So we're using the same examples that I showed you. We're creating the data here and plot them, and you can use a function in sklearn called trend testing split. So this can split your data by percentage. You can also set up the random seeds, so the split will be the same every time you run it. So now we want to keep 70% as training for both X and Y. And the other 30% as we call it remaining. And for the remaining, we keep splitting them by half. So our validation and testing will be 50% each. So now you have 3 data. And similarly, these are the same. We're creating the model architecture and define the compile using the sequential Keras API. And these are all the same. And you can feed the data. So instead of using the whole data, you use partially only the train, which is only 70% of your data. And you do the prediction. So for the prediction, now you can see we're using text data. And we can plot them out to visually see how the model performs. And you can measure the model performance by mean absolute errors or mean squared errors. So once you are satisfied with your model performance, you can save the model. So this is done after you feel very satisfying with the model's performance. You can define a model's path where you want to save the model and do the model save. This will save you the model into this folder. You can save only the model's weights and bias, these parameters, or you can save the whole model. Once the model is saved, later on, if you want to use it for inference, you can reload it by the Keras model.load model, where you save it and your model name, and you can use it without retrain it. So this is for this Jupyter Notebook. So do you have any questions before we move on?
If you save a model, and then you train it on more data, does the previous training get overwritten, or does it just add to the training set?
If you want to retrain the model with more data and you save it again, then the new model you saved will be different because you train it with new data. So you will expect the model's parameters will be updated. So your model will be different if you train it with more data. So I think Celso has a question about the difference between test and validation. So validation, it's used when you train the model. So when you train the model still will have access to both the training and the validation. But for testing data, usually it's not included in your training. So say if you have a model and you have well trained this model and save it somewhere, and maybe you can share the model to someone else who want to use the model. For them, all the data they have is testing, right? So testing data is really, you have trained your model already and you use the model for inference. Say if you have a model, you trained with say if you have a model that can predict product's price, right? You would like to use existing data to train your model. So mostly you would like to split the data into training and validation. But once the model is trained, you would like to have new data about the product and you want to use it for inference. So that's new data. It's usually called as testing data. Does that answer your question? Okay, great. So I guess I continue. So this is more examples. So it's still we're working on regression, but it's a real case example. So here I use examples from Kaggle. So the data is about insurance data. So we have some information, usually it's called features about like, for example, here it's a customers, and we want to have a model that can predict how much the insurance should charge. So here I import all the required packages, the dependencies, and then I can read the data. The data is the CSV data. So I also have this data in the Git repo. We can use a pandas read CSV to read the data into this variable called insurance. And you can see the top 10 lines of the CSV. So here we have 6 features, ages, sex, BMI, children, smoker, and regions. And we would like to predict the medical cost or the charges. So we're using the first 6 columns as our inputs and the final column as our targets. So remember in our last Jupyter notebooks, we would like to split the data into test, training, and testing. And now we're splitting them. Also for X, we drop the last column, charges. Right, the job is like deleting the last, because our X, which is input, it's only the first 6 columns. So we're dropping the charges columns in our X. And for our Y, which is our target, this is the last column. And we're splitting the X and Y by 80-20% into training and testing. So before we do the model for regression applications and neural networks, usually we do some pre-processing. One common one is min-max scalar, and another is one-hot encoder. And for column age, BMI, and children's, we're using the min-max scalar to do the pre-processing. And for sex, smoker, and regimes, we use one-hot encoder. So the min-max scalar is it's helpful because for each column, the data range is different, right? You want to have all the features, the values range are comparable to each other. So that makes the network easier to train. And for this three column, because the data of these three columns are categorical, but we have a regression application. So what we do usually it's using one-hot encoder, right? Because for example, regimes, these are values like southwest, northwest. You have to convert them into numerical values. So and the one-hot encoder is doing this. For example, if you have regimes, you have like 4 or 5 different values. If we encode them into like 0, 1, 2, 3, 4, instead of using southwest, northwest, this tax data. And similarly for sex, right? Female, male, maybe just 0, 1, 0, 1 for female, male, and yes and no, also it can be 0 and 1s. So that's how typical we do the pre-processing, min-max scalar, and one-hot encoder. There are also many other transformer or pre-processing. Like people also do log normal or Cox transformation. Like these are the techniques to make data more looks more balanced, like more like a normal distribution data. So this depends on your applications. There are many different ways of pre-processing. But for here we do min-max scalar, so the data can ranging from 0 to 1, and one-hot encoder. So after we do the pre-processing, so the map column transformer, it's kind of like stitching several pre-processing together. So this is how we do the this is what we're doing pre-processing. So after we are done with manipulating the data, we can start with neural networks. So here we use 3-layer neural networks, input layer, second layer, output layer. And we named the model to be insurance regression models. And the compile specifications are the same. We use mean, absolute errors, and atom optimizer, and matrix the same as MAE. And we have a callback. So this callback can be very handy. The callback is about early stopping. So when you train a model, you don't know how many epochs you should train it. You can shoot a random number, right? 20, and if you see the loss is not converging, you just, okay, let's retrain with 40 or 100. But this early stop can be very handy. You can give a very big epochs, right? That's the number of iterations for your training, and then you adding this callback. And once the model detect that, oh, the loss is converged pretty well, it's not decreasing anymore, it will stop early. Like here we define the model to fit 200 epochs. If the model, if a loss converges after maybe 40 epochs, the model will stop automatically. So this saves us a lot of time. So we start training, and we keep record everything of the training in the so-called history with this early stop callback. And you can see this is how the model's speed and loss and MAE metrics. So the loss is keep reducing. And after epochs 52, the loss function is not changing a lot in the last several epochs. So the early stop is triggered here, and the model stopped at epochs 52. So the training is done. And once the model is trained, you can do the prediction of the testing data, and you can measure the mean absolute errors of your model's performance on the testing data. So it seems our model have a mean absolute error of 3,000 and or about 3,200. In the history, you can plot the loss curve and see how the loss is reduced during the training, along with epochs. So the loss converged pretty well after epochs 50. So this is about a real example of using regression to predict the insurance cost. Do you have any questions? Okay, if not, I'll start with the next ones. So we work on quite a few times, a bit time on regression. Now I would like to give classification examples. So similarly, we import all the required package at the beginning, mostly NumPy, pandas, and to plot we use matplot library, and sklearn for preprocessing and TensorFlow. So here the data we have is generated by sklearn datasets. It's called make circles. What it does is it can create a data that looks similar to this. Looks this. Here you can define the number of data in your data sets, and you can plot them by creating a pandas data frame of the x, and so the first column is you can use it as x0 and second column is x1 and label it y. And in the plot, scatter plot, you can have this is color with the labels. So for different labels, you're given different colors. So the data in the outer circles, it's one label, and data in the inner circle is another color. So let's do this. This is how our circle data looks like. So it has two x columns, which is the position of your points. So x0 and x1s. That's the position of your points, and label. So we have create two labels. The blue and red, it's like 0 and 1s. So this is how our data looks like. So we can also see this is similar in regression. We create a model using the sequential API. So the difference that because now we have this classification model, the activation function at the last layer has to be sigmoid. So if you sigmoid function, I'm not sure if you so it looks like something like this. It will give you a continuous value between 0 and 1s, and you can have a cutoff, right? So the model outputs gives you a value of 0 and 1s, ranging between 0 and 1s. So if you final outputs say it's 0.8, and you can use a cutoff of 0.5, and then you can classify your outputs to be 1. If the output is below your cutoff of 0.5, let's say you got a 0.2 in your final output, and you can classify them as 0. So this is very typical activation function for classification applications. So again, here the model is very simple. It's just a 3-layer forward neural networks. And we also compile the model. So previously in regression, we're using mean absolute errors, but here we use binary cross entropy, which is a different loss to measure the performance for classification. So yeah, when we're dealing with different applications like classification or regression, or in image applications, segmentation, loss is the define of loss function is really essential for your model performance. But yeah, for two-class classification, binary cross entropy is very common. And similarly, we have early stop, and we can fit the model with early stop. And here I have an actual like utility function to help plot the performance of your fitted model by plot out the decision boundaries. We do not need to go through this details, But essentially, in the end, if you call this function, it will have a plot of boundaries of the models. In the you see that's a white lines circulating the circles. So for inlet and out, you can see the boundaries of the fitted model is doing pretty well. So for this classification, if you use some like tree methods or linear regression, a linear model, it's hard to differentiating the two class of points. But with a simple neural network, right? We only have a 3-layer of feed-forward neural network, and you can see the model performs pretty well to differentiating the two class of points. So similarly, we are plotting the loss and accuracy against the approaches, and you can see the model performs quite well and converged after like 20 approaches. So this is an actual example of how you can use for classification. Let's move to the next one. Oh, before I move on, do you have any questions for this classification examples?
For separating those two rings of data, if you wanted to make the boundary line cleaner, like with more bias where it was just a circle by itself, how can you like smooth out the decision boundary?
Oh, that's decision boundary. It's this is like a, so in the model, you do not have this, right? The models only can give you a classification. So the boundaries that I plot out, it's through this plot decision boundary function, which is an actual thing. So if you want to smooth out the boundaries, I guess you have a final mesh. Does this answer your question, right? You want the like the white lines to be more smooth? Is that what you want? Or
Yeah, but not just visually, like within the program itself, like to make the model smoother. Is that possible?
you make the model smoother,
Like by increasing the bias, so I mean it doesn't curve around so much. Yeah, I'm pretty new to Keras, so I was just wondering.
yeah, yeah, smoothness, it's hard to tell how we can fine-tune the model so the boundaries is more smooth. I guess if you train your model really well by fine-tuning it, the discrimination, I mean, the boundaries will more aligned along the center of the points, but it will not be guaranteed that the boundaries is more smooth or less smooth. That's really no boundaries when you do the modeling. So this is really we are using an actual function to help visualize the model's performance. I think one thing that can help answer this question is, so remember we use this sigmoid function as our last layer, and we say this will guarantee our model's outputs has a value between 0 and 1s. And we, by default, we use 0.5 as our cutoff. So there are also techniques that can help you to determine this cutoff. So it's not necessarily be 0.5. Something like AUC, I'm not sure how familiar you are with classification, but usually there are techniques that help you to find the optimal cutoff. So by doing this, your model's outputs will be tuned the best, so it can differentiate in different labels. I mean, the boundaries you will see, the boundaries here you will see will be wilder. That's one thing you can do.
That makes sense by changing the threshold. Thank you.
Yeah. Okay, that's a good question. Okay, now let's move on to the next Jupyter notebooks. So this Jupyter notebooks is about generator. You may not use it, but sometimes if your data is very big, you will find this very handy. So this is to say, if your data set is very big, some people working on tabular data that's like in megabytes, but some applications working on images or videos, and these can be hundreds of gigabytes. And then Python generators will be very useful because you cannot load every data into the memory. Usually, if you work on HAL, the GPU we are using is V100, and you're limited to like 32 gigabytes for memory. If you have data larger than, I would say, 10 gigabytes, you will find it's very hard to load everything at the same time, load every data into the chip, into the GPU and start training your model. It becomes impossible. So what we have to do is we create a generator that we load maybe only like 100 images at a batch, and we train the model with this first 100 images or 100 samples. It does not necessarily to be an image. And then once the model is trained, you load the next 100. So you're loading the data not simultaneously the whole data. Instead, you're loading the data in a batch mode, right? You start with first 100 and you train the model, and then you go to the next 100 and train the model again. And you continue doing this to reading all your data and train the model. So let's import all the packages. And so here I give example of a data set that's provided in Keras. It's called fashion MNIST. So if you do this, I say load the data of this fashion MNIST, it will give us automatically splitted training and testing data. And they are in NumPy arrays already. If you see the data type, it's integer 8, and shape shape, you can see for training, there are 60,000 with each. So they are all image data. The image dimension, the pixels are 28 times 28. And so for Y it's which is the label the images, it's only one label. So you can see it's 60,000. So training is images, and training in the X is inputs is images and outputs is a label. So the data is about like giving an image. We say, oh, this is a t-shirt, or this is a shoes. So various different kinds of labels. We can check the size of our training by say call this n bytes, and since it's in bytes, so we're converting into gigabytes, and you can see how big the data is. So it's about this size, and we can randomly visualize a sample of our data. So this is a skirt. Let's see what this looks like. Okay, this more looks like a t-shirt. Maybe a different number. I don't know. This maybe looks like a shoes. But that's a data. That's our data. And then we do the pre-processing. So the data we divide by 255, because in RGB it's ranging from 0 to 255. If we divide this is essentially, it's like a min-max scalar, so the data can be scaled into a range of 0 to 1. And our data is two-dimensional. We have 28 times 28. So it's only a two-dimensional image with one channel. There are 60,000 of them. But for most of the models to work with, usually we work with 3D images, so RGB is 3-channel. So what we do is we're adding additional dimension by call this new axis in the last channel, in the last axis. And now you can see the trend data has a shape of 28 times 28 times 1. Usually for images like we've taken photos, it's 28 times, it's more like this. It's like 10,000 times 10,000 times 3. It's much bigger. But you can see after we adding an actual axis, so converting the image from 2D to 3D, the memory is 100 times more. So it used to be like 0.04, but now it's 0.3 gigabytes by just adding an actual layer. So think about if you have more data, if you have like 100 times more of this data size, or your images has a much higher resolution. So instead of 28, you have 3,000 times 3,000. Then the memory will be huge. It's too big for any hardware to read in. And so that's why we need generator. So the easiest way, if you can read all your inputs data into memory, then you do not need to worry anything. What you do is you can easily create this data sets and convert them into tensors, and then use the TensorFlow data sets from tensor slides. This will convert your data into an object, a TensorFlow object. It's called a TensorFlow data set object, which is a Python iterable. It can produce a sequence of elements. So, for example, if we run this, we are calling this from tensor slides. So this is only a list in Python. And now you can call this iterable and print it sequentially. You can also call the iter on this data set. If you do this, like now you start from 0, the beginning. If I run this again, it will go to 1 and 2, and eventually go to the last elements. Okay, so let's see how we can create a generator for this data. So we load the data first, and remember we have images as X and labels as Y in our training, and we normalize it, and we change the data type from integer 8 to integer 32, and we do the same thing for testing. So now our data is ready. So it's the images and labels are all NumPy arrays. Now we can start to create a batch data sets by calling this data sets from tensor slides. We input the image and labels, and this will give a data set object, TensorFlow dataset object. And then for this dataset object, we say we shuffle it every 5,000, and we do batch 32. So now this is a batch. This becomes a batch dataset. So remember this concept is important. A batch is like we discussed before, like I mentioned before, it's the number of samples you use to update to fit into your model and update your weights and bias when you call the optimizer function. So that's the number of samples you fit in. If your input is images, that's like for every 32 image you fit into the model will call the optimizer to tune the weights and bias, and then you fit in another 32 images. It calls the optimizer again and re-update your parameters.
If you don't run the batch, will it just do one image at a time?
If you do not do the batch, for this batch dataset, you have to specify it. I'm not sure if that's a default value. I guess I can quickly check. But yeah, if you do the batch data set, so remember this is when your data is big, you cannot assuming you cannot load every data into the memory. If you do not do this way, the model will reading all the data it provides. So which may not be what you want. Also, even you can feed in all your data in your memory, it still suggests we do this batch way. There are reasons behind it. So we are using stochastic gradient as our optimizer. There are studies to show you that if you feed in all the data to train it, usually it will not easily find a global minimum if you feed all the data into it. Instead, if you feed in the model with like partially of a batch of your data, like maybe 1/10 of your data, and then you use the second 1/10 to iteratively update your model, your optimizer will not stuck into some local minimum. It has a tendency to go to a global minimum if you do the batch ways. If you feeding all the data into your model, so first you may not be able to do this because of limitation of the memory. Second, your training will easily be stocked into a local minimum for your optimizer, which means your model will not have a good performance.
That makes
So
sense. Thank you.
Yeah, in general, it suggests you do use these batch features. Well, this number is another hyperparameters you have to test. If it's too small, your data, your training, it's jumping around because the first, let's say if you use 8, the first 8 samples might be very different to the second 8 samples. And your training, it's kind of the parameters kind of jumping around. It's hard to get converged. But if this number is too big, it's more or less the same as not using batches, right? It's in practice, people use like 128 or 64 if you're dealing if you're working with image applications. But yeah, this is, keep in mind, this is something you have to fine tune it. Like you try it a couple of times and see which is the best that can give you the best model performance. Yeah, but okay, let's continue. I think I wrong this. Okay. So now if you see, if I just print this batch data set, you can see the shape. It's well, it says long, but if you if we want to have a pic of this batch data set looks like by calling the iter function and do next, you can see it gives us a batch data, right? So we have 60,000 in total, but for every instance of the batch data, the size is only 32, right? 32 times 28 times 28. So that's a batch data set looks like. If it will do this when you train the data, if it feed in only this amount of data into the model every time steps. Okay. So this is similar. We do the model, we do the compile. So you see now in the feed, when we feed the model, instead of the whole data set, the entire data set, we're giving this batch data set, and the model will like catch and feed data in a batch mode automatically. So this is about the a generator in terms of Python. If you start working with TensorFlow or PyTorch, you can you may start with someone's code, and you can see they will use this batch. This Jupyter notebook is help you to understand like why we're doing batch and how we do batch to feed the data. There are also many other ways. For example, if your data cannot fit in the memory, instead of reading the batch of the true data, you can name each of the data, and then what you fit in the batch data sets, it's only the name of the data or the path to the data. You can find an example here in the Git in the link I provide here. So with that, I think I'm pretty done with this, except the one final notebooks. So for this, it's that's a more advanced materials. The objective of this notebook is to help you, if you work with some like GitHub repo, work with someone else code, this might be helpful for you to understand how people do build their models. In TensorFlow, there are many ways of define your neural network layers or architectures. The compile part, it's kind of universal and easy to understand, but when I start with working with TensorFlow, I found it difficult to understand how people build their neural network architectures. There are many ways. You can see we give examples of Keras. That is very intuitive. But in case Keras does not have the kind of architecture you want to customize some layers, you can define your own layers by inherit the Keras layers and define your parameters like width and bias on your own, and then modify the call functions. So whatever x is the inputs, whatever you want, the relation between y and x, you can define in the call. And you can see in some advanced models, you can see this kind of features. Just keep in mind, not every layers are all defined in Keras. There are some unique case where you have to customize your layers, and then you have to redefine a class, a subclass. Let's see, build methods. Yeah, this is not critical. Let me see. There are also, in general, there are 3 levels of abstraction when you define the model. We give examples of using Keras sequential. You see a lot of like models you find in GitHub or other open source code. They are using this method. Very intuitive, right? You have input layer, dense layer, ReLU, activation layer, or convolution layer, or whatever layers. Sequentially, you're just adding them together. There's another way of writing this. now we're putting all the network architecture in one single list. You can also add in the each gradually in a separate lines by using the add function. But essentially, it's all Keras sequential model, which is a most intuitive way to build a network. Then if your model is not sequential, right, you have some nested or nonlinear topology, you can easily see other people using the so-called functional API, which allows you to have more sophisticated nonlinear network architectures. The difference is that instead of using sequential, for each next layer, you use the previous layer. At the end, you say, I do this on top of this layer to give me this layer. So sequential, so this is a sequential case, but this is the how functional API, right? You can see it's very different than the sequential way. So if you read some other code and you find like this is how they write, then you should know, oh, it's writing a functional API way instead of sequential way. This allows you to build long sequential models. Functional API. And finally, the subclassing, which we discussed before. You change you inherit from the Keras model and change it by customize on your own by redefining a class. So if you work with UNet, you can see a lot of people doing this ways. They stitch a few layers into a block and rename it as something like a new class. So that's another way of defining your network architecture. So there are 3 levels of abstraction to define. There are also 3 layers of abstraction for training. Even like training is very intuitive. Like mostly you see just like model.fit. This is a default way of people how fit the model in TensorFlow, right? Define the 3 optimizer, loss, and metrics in the compile, and you can just call the fit function. But if you have multiple outputs, then you have to define your loss into a dictionary and the matrix as well. And sometimes you have to customize the fit, right? The default ones cannot fit your need. You have to fine tune it. Then what you have to do is you need to override a method in the fit. It's called train steps. We're providing examples here. Also, you can override the matrix as well. You can, so yeah, so this is really like you can customize the fit. So instead of using all the default ones, you can tell the fit function how to train it. Again, these are all advanced materials. If you find this in some open source code that you find difficult to understand, maybe use this as a reference. So with that, I think I'm done with today's workshop. And thank you again for your attending. If you have questions about any of this, you can email me or Slack me, drop a message in the Slack channel. I'll see you in the next.
Thank you.